In this video, we're going to look at our last application of nonlinear optimization. And so in the previous two videos, we looked at applications inside of finance, creating an index fund as well as the Markowitz portfolio model. And in this video, we're going to take a little bit of a different route and look at a forecasting application. And specifically, we're going to look at implementing the Bass forecasting model by Frank Bass. And so the whole idea behind this model is that you're wanting to forecast the adoption of some new product. You launch a brand new product and you want to know how sales are going to go, for instance, over the first few months of the product's life there. And so the way the Bass forecasting model works is that we have three parameters that we are trying to achieve values for. M, P, and Q will be the variables that we use in this application. And M is basically standing for the number of people that will eventually adopt the product. So if you think of all the people that will ever adopt your product, M will be that value. And then P and Q have to do with the adoption rates and different things that can influence someone's desire to adopt a product. And Q is called the coefficient of imitation. And so this kind of comes down to like peer pressure a little bit, or word of mouth. You basically have a friend that adopts the product, they start talking about it to you, and it's trying to capture that motivation that may be imparted to you to adopt that same product there. And then we have P with the coefficient of innovation, and this is basically the influence of the product as it stands by itself with you wanting to adopt it. And so it needs no word of mouth here. You basically look at the product, you see an ad for it and say, wow, that's a great idea. I want to look into purchasing that. That would be the idea behind coefficient of innovation. And so we use these two variables in order to come up with a likelihood of adoption. And so if you look at the formula here in the middle of the page, we have the p-value just all by itself, which kind of makes sense because it's that innovation term there. It doesn't have any other dependencies other than the product itself. And then on the right side of the addition is a product between the coefficient of imitation and this fraction here. And notice the fraction is got the total audience number in the denominator, and c to t minus 1 is basically the quantity of people who have already adopted the product through some time t minus 1. And so if you look at that fraction, you think of that as the fraction of the total number of people that will eventually adopt the product. We multiply that by the coefficient of imitation, and that is a good indicator of like kind of how many people are talking and the effect of that noise, so to speak, on the remaining population. And then we also will use this sum in our forecasting expression. And so what we'll end up doing is it's a forecasting problem, so we'll be looking at independent time steps and trying to predict the amount of adoption at each one of these time steps moving forward. And so on the left-hand side of our adoption expression here, we've got a product, as you can see, and the left-hand item on that product is just this adoption likelihood. You can see this expression is mapped right down in here. And then on the right-hand side, you have n minus c sub t minus 1. If you think about that a little bit, that is the remainder of the population of individuals that have yet to adopt your product at time t there. So it's the remaining group of people out there that you're still trying to influence and still have adopt your product. And so what we'll end up doing is we'll make continued forecasting calculations as we move from time period to time period using this expression. And so you say, okay, that's good. I kind of understand where we're going here. We're going to forecast some values out. Let's actually see the model now. And so that's what we're seeing here as I page down the notebook a little bit. Obviously, we'll have a set of time steps t, t1, t2, t3, t4, so on and so forth. Depending on the problem, that could be days, that could be weeks, that could be months, years, so on and so forth. And then what we're trying to do is you can see we're trying to attempt to minimize some error term here. And so let's first jump down into the constraints area, and you can see this block here saying for every time step in the set of times, we're going to compute some error term. And what that error term is going to be the difference between our forecasted value, that'll be f sub t, minus the actually realized value, S sub t there. And so between that, we can find a difference, how bad our forecast was compared to the actual recorded value. And then we'll compute that for every time step. And then you can see our expression that we're trying to minimize is the summation of the squared error terms there. Obviously, if I square the error, then I don't have to worry about kind of negative error values artificially canceling out positive error values there. So that's hopefully all sounding good. This top constraint here is just an implementation of our forecast expression that we previously talked about. And again, we'll be doing that for every time step t. And finally, am's got to be greater than or equal to 0. That intuitively makes sense, right? That's talking about the amount of people that will eventually adopt the product. Obviously, the lower bound of that is no one adopts the product, and well, that's kind of a sad day. All right, so with that being said, let's go ahead and just kind of talk through the Python bits, because they do get a little more complicated just because of the amount of data that we're working with, and then we'll see about implementing something similar in MS Excel. So to make this a little more tangible, let's look at forecasting independent studio films. So let's say you've got a film, you're getting ready to release it to the theaters, so to speak. And we want to be able to forecast the revenue that's going to be generated over the first few weeks or first few months of this film being introduced. And so that's what I have here in this sales data frame. You can see it's indexed off of the week, so we're just numbering weeks 1 through 12 there. That'll end up being our time steps. And then we're going to have recorded the revenue that's generated for each week. And so that's what you see as the second column here. And then the third column is just going to be the cumulative revenue. So for instance, in week 2, you've accumulated 3.1 units of revenue. By week 4, it's been 15.3, so on and so forth there. And so that's the data that we have to work with. This cumulative revenue, that'll be playing the part of C sub t. When we see the C's in our model, and the revenue terms will be this S part of the model. And so essentially we're going to use this data in order to fit, if you will, values for MP and Q. And so one thing you may be asking yourself is like, hey, I'm forecasting for some time period, but I'm having to wait for the time periods to actually occur in order to develop the model. And you're saying, well, that's not going to be a very good forecast, right? Because it's already happened. Forecasting is trying to predict into the future. And yes, that's a natural thing to say with the BAS model. And so there are two different implementations you can use the MAS model for. One would be the idea of you have a movie that comes out this summer, for instance. You record all this data. You then use the nonlinear optimization to come up with the values of MP and Q. You wait basically till the next summer and say, well, I've got a similar type movie. It's coming out at a similar time of year. I assume that the same MP and Q values are valid, and then use those MP and Q values as inputs into the model for your next movie. Another thing would be to do it kind of incrementally in nature. And so what that means is use the data that you have, say, at week 6, run your model, determine the coefficients, and then try to make a prediction for week 7 and 8, essentially. Just making very short horizon predictions there, and then continuing to do that incrementally as you progress week to week. All right, so with that being said about application, let's go ahead and actually see the mechanics of how we implement the model in Python. So first off, I've got a little bit of markdown text here just showing what it's going to look like for these specific problem. And again, we have 12 time steps, so you can see the minimization of the squared error terms. That's time steps 1 to 12. Subject to, then we have all of our forecast values. And notice here I'm writing something a little bit different for the initial forecast, the forecast at time 1. And all I claim is it is P times M. But we actually saw a formula that looked about like this for the forecast discussion above. And really the same thing is valid, just because if you look at this expression here, notice it references the cumulative amount of adopters. We're using the sales as an analog for that in the period before. Well, if I'm in the very first period of introduction, there is no adoption in the period before, so that would be 0. And if I have c sub t minus 1 being 0 in these expressions, the only thing that's left is the product of p and m. And that's why you see there's a little bit different start of the forecasting model, just in p and m, and that's kind of what gets everything started moving forward. Then for all the other ones, you can see for times 2 through 12, we just implement this expression for the forecast at that time. And then notice our error term is the forecasted value minus the actually recorded value. That's good. For times t equals 1, 2, 3, all the way through to the end. And then we have our bounds there. And so that all hopefully makes sense. And one of the things, if you start looking at this, is that this is not going to be quite as nice, so to speak, as our other examples. The other examples were all convex or concave. So the way to solve those is fairly straightforward. You can run a gradient descent algorithm on it, and you are guaranteed to know that the solution that you arrive at, if it's a local optimum, will also be the global optimum there, just because remember those convex and concave shapes are kind of bowl shaped there, so that helps us to know that when we stop our solver at an optimum, it is the global optimum. In this case, we don't have that, and I guess when you look at that, you can see it. Probably the best place is here, is you're going to end up showing there's going to be products of your decision variables. And I guess the best way I can see that is if we work from the top, we've got an error term that is squared. Inside of the error term, we have this forecast term. And if we look at the forecast term here, notice when I go to quote-unquote FOIL this expression out with the first terms times each other, I already have p times m. I've got p times m right here actually in the first forecast step as well. Well, that would be a product between two decision variables there. And that right there in and of itself breaks down our definition for convex and concave functions. So basically what we do is we have to be careful then about when we see a solution, is it optimal or not. And so this is where you're going to see me come down below here, and I'll be using a different method of SciPy than I had before. Specifically, I'm going to use the differential evolution solver, which the documentation's right here. You can see it finds the global minimum of a multivariate function, and so that's great. We have 3 variables that we're trying to work in our function, so that should be fine. It is stochastic in nature, and basically what it does is it's going to be implementing some sort of genetic algorithm underneath it. And so if you haven't heard of genetic algorithms and are definitely interested in this type of stuff, I would strongly suggest you watching this lecture from Patrick Winston at MIT's OCW. It's right here. You can kind of see the course number 6.034, fall of 2010, when it was recorded. He does a very good job of describing the different elements that can be found in genetic algorithms there. And so if you're interested at all, I strongly suggest this. Totally optional as far as for the class requirements, but again, it is a very interesting lecture. And so we're going to use the SciPy method in order to run such a thing. And we'll just slide down here to see some of that Python code. And so you can see most of this I've implemented inside of a function. It's called execute forecast search, which is defined here. I'm passing in the entire sales data frame, and then I've got bounds for M, P, and Q. That's one of the requirements here. Notice I've got bounds for variables is a required parameter inside of the differential solver there. And so I'm fairly liberal on my bounds, as you can see. I say M can run from 0 to 1,000, and then I'm specifying the P and the Q values ranging from -10 to 10 in this case. And I've got true for coming into the display optional parameter. That just comes down here, and I believe if you read the documentation, that's just going to have it spit out these intermediate values as the genetic algorithm goes through its process. As far as what the genetic algorithm actually is doing, just to give a little bit of highlight overview, it works off kind of the basic principles of evolution, as kind of you can think of like Darwin's evolutionary theory. And so basically you start off with a population of candidate solutions. And in our case, a candidate solution would be a tuple of three values, one for M, one for P, and one for Q, and you randomly seed the population. And then what you do is you have some function that you're trying to improve, a fitness function, if you will. And in our case, that may be an error that we're trying to decrease that we'd have to write in as a way to have it improve that way. And so what you do is you basically have this population, it's randomly seeded, you've got a fitness function that you can judge the fitness on each one, and then you go through some sort of selection process where the fitter candidates are the ones that you keep on to the next generation. Then everything else has a high probability of moving on to the next generation. Then what you do is have a crossover event where you take two different candidates and you cross over them as far as exchange what would be genetic material from one to the other. Those produce children candidates that then go into the next generation, and then you move forward generation after that. And so at each generation then you basically start hoping to improve on your fitness function overall. And so generally you would keep track of, for every generation, what is the highest fitness function you've achieved, and then also kind of the average fitness level of the entire population. And you'd hope to see that fitness function become better, increase or decrease, depending on whether you're trying to maximize or minimize something as we move forward. And so that's kind of a short little bit about the theory of what's going on. And so the actual implementation here in Python, I basically grab the values of the data frame in which the weeks is in the index. So that should just be the sales and the cumulative sales. Then I've got a function that's listed here, which just determines the squared error itself. The bounds that are passed in are brought into a list, and then I pass that into the SciPy function and then return the results of the SciPy function out of my own function here. And then if I run this, you start to see the fitness function basically decrease as I move forward. These should be the result of the squared error terms. You can notice they start off quite large, but then as the solver progresses, they get smaller and smaller and smaller until it becomes terminated at a value of 14.496 for the squared error term. Then, just like all the other results that came out of SciPy, the X property holds the parameters, and so in this case it holds the M, P, and Q in positions 0, 1, and 2 there. And so we would say for this specific application, our M is 34.8, P is roughly 0.07, and Q is 0.49. And so that would give you a feel, again, for the total audience that's going to adopt your product, the coefficient of imitation, and the coefficient of innovation there. And so if I come down here, one of the things you may do with this is see the matching of the two models. I should say two data series there. In one sense you have the recorded values, which is what's in the blue trace here. And then in the other sense you have the models predicted values here in red. And so you can see it's fairly well capturing this rise and fall of the sales for this independent studio film, where that peak is happening right around week 4 there. Okay, so that's the discussion inside of the notebook with Python, and let's see about implementing this as well inside of MS Excel. So I'll go ahead and put these side by side here, and one of the things I'll want to be able to see as I work through this is our model, and so I'll just leave it about like that. And so I've already transferred the data as usual just to cut down on a little bit of time. And so if I start working over in Excel, what I want to start with are the decision variables. And so we have M, P, and Q as the decision variables here. I'll just make those a little gray. We'll also have an objective function that we're going to try to minimize some squared error term here. And then we'll have our typical constraints that we have down here. Alright, so we need to come up with some forecast values. So they happen at every time. So I'll just grab this here, and I'll say I've got a forecast here. And so the forecast for the first time period is just P times M. So I can just put that here. And then for all the other time periods, I'm using this expression here. It is what? In parentheses, we've got P plus Q times this cumulative value from the time step before. So I'm at time step 2. My cumulative value would be the time step at 1. And I divide that by M. And I have all that times M minus, again, that cumulative value. Alright, so at this point I believe we need to lock some cells up. It appears just the cell that's in row 4, that D4. Oh no, not D4, we don't want to lock that, that's the one we need to float. We need to lock everything in 20, row 20. So I'll go ahead and lock these all up, and then we'll float D4. That way as I move down here, those stay put, and I continue to reference the cumulative revenue in the week before. Alright, so that's looking good. Now we need the error squared term here. So if I look at this, the error term itself would be forecasted minus the actual sales in that week, and then we would square that for the error squared term. And it looks like it's dragging down as appropriately. And then we would sum all the errored square terms in our objective function. Okay, so now that we have all that in place, let's go ahead and get into the solver. So I can go to Data, Solver. I want to set this as the minimum. I do want to minimize this. So I've got the object function, I've got it minimized. I want to go relative to these values. And similar to over here, I'm going to treat this with the evolutionary solver and give that a go. One of the things, just like in here, we need to have bounds for our variables. So let's add in here and say this M value, I don't know the units on these, so let's say it's got to be less than 100. The Q value less than 1, and the P value less than 1, and the Q value also less than 1. Sorry, misspoke there. Let's try that, and we'll go ahead and make the unconstrained variables non-negative to give it the lower bounds there. And then also I want to go into here into the solvers just to make sure we're not waiting too long. So I'll go to the evolutionary tab, and what I'm going to do is I'm going to change this default value just because we're in a video here, and set that at 10, and I'll bump the population size up to 100. All these things about mutation rate, population size, and the random seed, that's all stuff that is obviously specific to evolutionary algorithms and the genetic algorithms as well. That's one way to talk about that. So we'll hit OK, and I think we're good to hit solve. Alright, so notice it said setting up the problem real quick, and now we are off and running. You can see in the bottom left hand side it kind of hovering around a little bit. You can see the incumbent. That should be the resulting fitness function of the best solution as we've got so far. It's going through all these sub problems here that it's basically going as it goes from generation to generation in the search for a solution on the genetic algorithm, and then eventually it cannot improve the current solution. So essentially we've got these termination conditions built in there. In the options you saw a convergence, which is probably about a measure of the amount of change from like generation to generation. How much has the incumbent changed there? And then also I think I put down 10 seconds for the timeout, basically saying, hey, if you're continuing to run this thing and it goes 10 seconds and you haven't improved the fitness function, then go ahead and fall out at that point. And so we'll just accept what it has for us now, and we achieve, I think, the exact same values we got inside of our Python notebook there. So let's slide down here a little bit. Here we go. The function terminated at 14.496, that agrees there. M is 34.81. P is 0.07 and Q is 0.49 there. So very good. We've achieved the exact same model parameters using both SciPy's differential evolution method as well as the evolutionary solver inside of MS Excel there. Also, just so you know, this method I'm using in Excel is slightly different than the workbook that I posted on Canvas as well. I think it uses the GRG nonlinear solver, but does a multi-start option in there in order to arrive at the optimal solution. All right, so with that being said, hopefully this gives you a little bit more of an appreciation for nonlinear problems. You can kind of see some of the intricacies that happen when you don't have just convex and concave objective functions that you're working with. And I've also been able to show a little bit of differences in the solution methods you have. Both in Excel, you can go ahead and sometimes dip into that evolutionary solver, and then also we've shown again the differential evolution method inside of SciPy.